if, if, for instance, there's some emergency, there's a fire alarm that goes off, then it's necessary for you to take control of the room, okay? So one of the things that you'd need to do is to make sure you've got the microphone. So you go to room controls, hold on, room controls. Ooh, that's interesting. Room controls work. Wow, that's amazing. Oh, well, let's have a look at the microphones. Okay. So what you need to do is to make sure that that's working. Okay. So that you can then make an announcement. I'll just.
Oh, good.
Yeah, I'm about to start.
Yeah, absolutely.
Okay.
Now, if you move out of frame, the focus on the canvas disappears.
I see, and it refocuses and
then
takes
it
some time.
refocuses. And apparently, if you stay in the one position for too long, it tries to refocus as well. So,
Okay.
but I'll try and get a sense of
So I gotta keep moving? Is that what you're saying?
hoping that's not the case.
All right. We'll probably get started. Thank you. If this is even working. Hello? Okay. No, it is working. All right, so we'll probably get started. Sorry, first of all, people at the back, can you hear me okay? All right, good. Yeah, okay, so thank you all. First of all, thank you all for coming. I know it's a Monday lecture, and look, Monday morning sucks. I had to skip breakfast myself, so it's good that we're all here. A warm welcome to you all to the first lecture of semester 2, I guess. And for most of you, this is probably the first paper that you're taking that's offered by the Department of Electrical, Computer and Software Engineering. So a warm welcome to you all. Now, at part 1, we are just dipping our toes into a bit of everything that the faculty has to offer. So you've all survived semester 1, which is great. You see, this is an exciting time. I am excited for what's ahead of you. You are all, or at least most of you all, are sort of halfway through the first year of a proper degree. You are here, I guess, because you like technical things. Yes, you like solving problems. There's something about the technology that attracts you. You see, electronics is an enabling technology. It enables people to do things. If you haven't realized, everything in the society is controlled by electronics, right? Gone are the days of horses and donkeys doing our dirty work. Now if you look around, we have electric scooters and hoverboards everywhere. So there are all sorts of things that you are going to learn, and for that, I am excited for. But in case that nobody has told you yet, you don't actually learn everything at the university, especially at the undergraduate portion of your degree. And that's simply because it's simply not possible to cover everything in a degree, let alone a course. And this is especially true for engineering because the pace at which developments are made has become so frequent and rapid. Right? It's only in 2010 when when smartphones became mainstream, and to now, you know, driverless cars is actually a thing. Right, so what that means is to say that one can essentially cover a subject in this ever-growing field, I feel we'd be doing a pretty big disservice to the rich discoveries underpinning the transformations that engineers are bringing to our everyday life. What that means for us is that engineering at the university, the goal of it is really about uncovering rather than covering a subject, right? You see, all we're doing is equipping you with what I like to call the tools of the trade necessary for you to start exploring, to question, or to reason about problems to which we haven't actually solved yet. You see, engineering as a profession is built on solving societal problems to which a solution does not exist yet. So by the end of your degree, that should be the sort of problems that you are good at finding answers to. Now, engineering is also an endeavor where everything is built on top of everything else. So this is not like in CEA where, you know, you could say to yourself, I'm just not going to worry about that particular topic. You see, the ideas that we are going to cover and also the subsequent specializations that you go into relies on a firm understanding of earlier exposed concepts. So it's especially important that we get these fundamentals right, for without a firm footing in these, it will simply be impossible to understand, let alone engineer anything useful. Now, lest you think always in chaos, what did you get yourself into? It's not that difficult. All that required is a little bit of consistent effort on your end. Right? This is not a subject where you can cram. Right? It's not like in CEA level 1 geography, where you can leave everything to the last minute. Right? There are ideas that's going to take time to absorb and sink in, and we definitely want to save you from having a stomach ulcer or a brain aneurysm at the time of the exam. And so we have deliberately set out the coursework to provide that opportunity for you to engage in this persistent habit or effort. Right? So if you look at sort of the course planner that's available to you on Canvas, there are essentially 11 assignments in this course, one of which is the Fundamental Circuit Concept Tutorial, the FCCT. Now that's already available to you since last week, if you follow the announcement. Now, these assignments are online, and obviously they are sort of weekly assignment almost. They are rather low stake, and you can do them anytime you like. Obviously, provided you complete them within the deadline, which are usually on a Sunday. Now, these assignments cover topics from usually the materials covered in the week prior. Now, you can do these assignments anytime you like. There's no time limit on this. You can attempt the questions as many times as you like, provided that you get them correct at the end. You won't get the marks for it. Now, so hopefully you see the whole idea here is to encourage genuine attempts, right? It's allow you to interrogate your understanding of these underpinning concepts rather than seeing them as assignments as a mean of optimizing for marks. Now, before I move on, I'd just like to make mention that these assignments, they are ran online, and they are hosted on a platform that's developed by my esteemed colleague Bill, and Bill's back there. And he would just like to talk to you a little bit about the platform itself. Thanks, Bill.
Good morning.
That's a very evil introduction. Oh no, I think I turned that off. I think it was that. No, maybe it is you. Now I'll turn my...
Okay, good morning. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ka monga kiki te monga, ka manukau te moana. Ka Ngāti Pākehā te iwi, I wehe o tūpuna I Norway. Ko Collis toko whana, ko Bill toko ingoa. E engineer aho, he kiako aho. Kia ora, tēnā koutou. So my name is Bill Collis. I'm, along with William, my esteemed colleague, one of the lecturers in the course. I'm an engineer and a teacher. I've spent about over 20 years as an engineer in various industries. Shout out to anyone who was in the military. I was in the Air Force for 8 years. And then I took up teaching electronics at a high school. Anyone from Mount Roskill? I was there for 14 years teaching electronics. And I came here in 2015, and my research has been around trying to help students understand electric circuits, their fundamentals, and what happens inside an electric circuit. And so I developed the software Gecko that you're using, and it's a reasonably stable platform. However, I wrote it, and although I am what they call in industry, I work across the stack, I work at various levels of software and hardware development, I would suggest that you don't leave your assignments until the last day they are due before you do the work on them. Now, this should flick to the document camera. Is that right, William? That one. Now it is. Thank you. Here's a typical graph of activity of students' assignments. Now, I will tell you that there is a reasonable correlation between marks in the course and how early you start your assignment questions. Now, that doesn't mean to say that there is a causation in this. It means that there is a correlation. Either the people who do well in the course do well anyway and they just start their assignments early, or those who start their assignments early do well in the course. I can't tell you which way around it is, but definitely on a Sunday night, at 11 p.m. when the assignment tool is turned off. Up until that point, for instance, during this assignment, which was assignment 3 last year, we had people doing 13,000 submissions to the assignment that last day. Okay, so it does all right, but I would suggest that maybe if you can, and I understand the pressure you are under and you are going to be under this semester with your courses, that it's not actually always feasible to do your assignments up front and early. When things go wrong, though, on a Sunday night, I would suggest that you breathe. Don't hold your breath for too long. Relax a little bit if you can. I know the time pressure is counting up on you. And you may be able to find some help on Piazza, but you may not. On a Sunday night, I'm often preparing for my work, which is going to happen on a Monday, or I'm out, and so I may not be able to help you until Monday morning after the assignment is closed. So I suggest you get in early if you can, and if you can't for that reason, get in early and something bad happens, which generally doesn't happen but does happen on occasion, then, well, you'll just have to live with it, I'm afraid. Yes. So welcome to the course. Later on in the course, when I start looking at how to use the fundamentals of electric circuit theory and the techniques of circuit analysis with some particular circuits, I'll be building a few little practical ones and showing them to you. If you're interested in doing that, I've put together a wish list of parts on AliExpress, and on page 155 of your course book, there is a link to that wish list. So you'll have to look at the PDF copy of the course book to see that. I also highly recommend that you get involved with the Unleashed space in the bottom of the engineering building. If you've not heard of the Unleashed space, the maker space, I suggest you get involved with it and make things. It always helps to solidify your understandings. So welcome to the course. That's all from me, and I'll hand you back to William. Kia ora.
Sorry. All right. Thanks, Bill. So I am William, by the way, in case you haven't realized, not just some random Asian guy. So there are essentially 4 lectures a week, as you have probably seen. Obviously, you're here today, so you know there's one on Monday morning. I will be taking the first roughly 4 weeks or so of the course before Bill takes over for the next chunk, and then I will return a bit for a week or so, and we alternate then. The one thing that I would like to mention is the laboratories. So you'll notice there is one laboratory in this course, and this happens in week 8 and 9. So when you first enrolled to the course, you would have selected a laboratory stream that you would go to. You only need to go to that lab, that stream. You do not need to go to each single lab indicated here. Now, the reason I'm bringing that up is you might also notice on student services online that you might have a laboratory in week 5 and 6. That is not actually running. The only reason it's there is because of historic scheduling. So it's not running this year. So there's no labs in 5 and 6, and there's only one in 8 and 9, depending on which stream you've enrolled to. There are also 2 tests in this course. The test dates, unfortunately, are set, so we cannot make any changes to that, simply because we have to cater for all 1,000 of you in this course, so the room requirements is all set. What that means is if you do have clashes or some sort of logistic or administration issue, please do contact the course coordinator, which is Bernard Gulliman. So Dr. Bernard Gulliman, he's the person who made the announcement to you earlier last week. But if you want to know his detail, it's also accessible under the administration module in the document that's course outline. So his detail will be somewhere down there. There you go, Bernard Gulliman. So feel free to pop him an email, and he'll obviously get back to you as soon as he can. But keep in mind that there might be an inevitable delay, given that there are 1,000 of you and only, or essentially 3 of us. In terms of the course book, if you haven't already done so, the course book is available at the university bookshop for you to purchase. Now, it's essential. We do highly recommend that you do get a physical copy, simply because we will use the course book extensively throughout the course. If you sort of briefly flip through the course book, you'll notice there are places where we would expand on or fill gaps in. But a digital copy is also available to you under the course module, the administration module over there, in case you prefer using tablets or whatnot instead. Recommended text. Now here's the recommended textbooks that you're not going to buy. But look, it's always a good thing to consult multiple sources when it comes to understanding a new concept or a new idea. And these are essentially the few texts that we actually found to be a rather intuitive introduction into the concepts that we will make use of throughout this course. Now, because you're not going to buy it, I have actually requested the library to provide a portion of the digital scan to these course textbooks, obviously up to the allowable allowance, right? So you could access these under the reading list tab and, just click view online and they will be available to you. So, make the most use out of these. Finally, the last thing I would like to mention before we actually, get underway with the course is Piazza. Now, for all those of you who were here in semester 1, you'll know what Piazza is. If you don't know it, for those of you who are coming here for the first time, essentially Piazza is this online forum where you are able to make anonymous posts, whether that be questions or discussions you would like to have about the course. Now, you'll know that I do monitor Piazza quite frequently, and that's simply because I believe learning is what happens outside of the lecture, right? And I do want to facilitate that environment and engage in learning outside. I like questions, right? And if there's some things that I say in class that's completely rubbish or makes no sense to you, feel free to ask me during class or after class or simply on Piazza, right? For those of you who used it, you'll sort of know how active I am in maintaining it. Look, I know there's a reluctance at part 1 to ask questions because, you don't want to lose your dignity, right? You might think that you know nothing and that you're the only one that know nothing. That's just crap, right? Chances are, if I said something that's rubbish and you're confused, half of the class is probably just as confused as you are. So really, your reluctance to ask questions really decreases over time, provided you try. It's almost like going to the doctors, right? The first time you go to a doctor with that huge hemorrhoid up your butt, right, you're not so concerned about the hemorrhoid itself. Rather, you're more concerned with, who else is going to find out about this, right? Am I going to wake up the next day seeing my butt on Facebook? Right, and you know what? By the 10th time you go again, you stop caring. You'll be going and saying, right, so you want my butt where? Right, because it's more important to have that issue resolved rather than what the issue actually is. Right, so don't be afraid to ask questions. Look, don't be afraid to get stuff wrong. I get stuff wrong all the time. But you know what? The experts in the world are the ones who have made the most mistakes, right? It's only when you make a mistake and learn from it, that's when learning actually happens. That's when you get better. I know that's not an experience you want to have during a test or an exam, right? So there's no better time to start than throughout the course as we progress. I think that's as much as I want to say in terms of the logistics and admin issue. Are there any questions so far? Oh, one thing I forgot to mention is with the lectures, now you'll notice that there's only one stream, right? So unfortunately, we have to distribute all of you over 3 lecture rooms. So if you look at the lecture rooms, they're essentially at the main lecture room here, the 260-098, but there are also 2 other rooms that's actually running simultaneously right now. That's an OGGB 3 and 4, which is just next door. These are receiving simultaneous audio and visual feed from this room. So feel free to attend any of these overflow rooms as you see fit. Some people actually like it more next door, but you might prefer it here because, you get to see me in person. I'm not sure why you would want to. But so that's something to keep in mind of. And that's it. Right. Any questions? If there's none, then I will probably get the course underway. So what I would like to do for the remainder of this hour is just to give you sort of a broad and brief introduction into why, as engineers, we are interested in electrical and digital systems. And in fact, what sort of electrical and digital systems am I talking about? And essentially giving you a helicopter view of what this course is about and sort of what you can expect to come for the rest of this course. Now, so if I get you to just turn to the first page, essentially, of your course book, and I'll flip the document camera over. Oh, you can't see anything. Right. Okay, so let me just start off by saying, thank you. Let me just start off by saying most of you will probably not go into a specialization in which you will design electronic equipment or instrumentations directly. But no matter what specialization you go into, each one of you will be using, or at the very least dealing with, electrical instrumentations. And the simple reason being because of the way our technology has advanced, that electrical technology has become utterly pervasive to the point that it almost resides at every corner of our everyday life. Right? If you haven't realized, we rely on electricity for literally everything, to the point that we are rarely conscious of its effect unless a device or systems fail or cease to function. Now, can I give you some examples? Probably. Say, if you press that power on button on your computer, well, you expect the computer to turn on, right? You expect to see the display showing your Microsoft or Apple logo, and before you know it, you're probably on Facebook making the next meme about Elec 101. But of course, what you don't think about is how that display that's connected to the graphic processing unit of your computer is actually able to interpret the signals that it receives, which is just voltage and current, by the way, and able to manipulate it into a form that it will display something that we can actually understand or comprehend. Right? Similarly, when you double-click that final season finale of Game of Thrones that you've just pirated last night, if you haven't seen it, I won't spoil it. Iron Man dies. But you would expect the media player to immediately render that video, and before you know it, you're probably having a blast, right? But what you don't think about is, well, how does the media player actually interpret the data that you've downloaded, whatever that means, and be able to produce audio and visual in a way that's intelligible to us, humans, right? But of course, you could argue, well, you are really unconscious of these things because it is expected that they would just work, right? These are consumer products in which they are designed to work. You wouldn't be buying something that doesn't work. But you see, as engineers, for the most of your time in your future career, it's actually the other way around. Because you will be using these equipment or instrumentations in situations for product development where it is expected that things are going to fail, that things are going to go wrong, because you are a part of that product development for these consumer products. Right? So it's in these situations that we want you to have a critical mind, that to be able to narrow down the problem. Is it the electronics that failed, or is it the environment in which you're using it that has gone out of control? What that means is, irrespective of what specialization you're going into, you are going to interact with people in your company that either design these electronics, or at the very least, you'll be dealing with third-party suppliers who design them for you. And in order for you to have a meaningful conversation with them, whatever that means, well, each one of you must have at least a bare-bone understanding of electrical and digital systems. And that's essentially our role in this course, to give you that bare-bone understanding. Now, you might say, hang on a minute, right? For the specialization that I'm going to go into, I'll probably be dealing with non-electrical quantities, right? For example, if you're thinking of getting into civil engineering, well, you might be interested in the stress or strain in a structural member, say in this lecture room, or the one next door that's going to be built by the end of the year. Similarly, if you're a chemical or material engineer, well, you might be interested in various temperatures at different chemical processes, right? So if I'm interested in those quantities, why do I need to know about, well, electrical instrumentation, right? Why can't I just use, for example, a mercury thermometer to read the temperature in those chemical processes? Now, hopefully you know the answer is quite obvious, right? Because, again, as engineers, we are not interested in these quantities just for the sake of measuring them. We're interested in these quantities in order for us ultimately to control, regulate, or ultimately manipulate them in a form that to get them into the value that we want them to be. Right, so you certainly wouldn't want to be a guy who stands at the chemical process reading the mercury thermometer and saying, oh, temperature's too high, I'm going to increase the temperature. Oh no, it's too low now, I'm going to decrease it, right? Ultimately, we want that to be done automatically, right? In other words, we want some sort of system that does this automation for us in order to maintain the temperature, for example. And you know what? It turns out the best way to do this with modern technology is through electronics, instrumentation, and equipment. And the simple reason for that is because we have such a thorough and complete understanding of electrical phenomena. You see, the great minds before us have invested a great deal into understanding electricity and electrical principles that we have such a concise and accurate understanding of what, for example, current and voltages are, right? We also have a precise way of knowing how to measure these quantities, how to transport charges from one way to the other, how we store these charges, or even regulate the energies on these charges, right? And we do so, as you would probably anticipate, all through the use of electrical circuit, right? And so, because we understand the electrical behaviors so well, and we can control them so well, that it turns out when we are interested in these non-electrical quantities, for example, temperature, that I was just referring to, well, it's actually very useful for us to actually use electrical quantities as stand-ins, or as what we call analogs. Oh, yes. Oh, sorry, you cannot see. My bad. Right, so again, because we understood electrical principles so well, that we know how they behave so accurately, that it turns out if we're interested in monitoring, say, the temperature, or even just the stresses in the structural member of this building, for example, well, it's extremely useful to simply convert that non-electrical quantity into an electrical equivalent. So this is what we call essentially an electrical analog, right? It's analog because of the word by analogy, right? And we use this analog to manipulate it and ultimately use it to control, to take action in order to control the original non-electrical quantity that we are interested in, for example, temperature. So the example might be, if we're interested in regulating this temperature in a chemical process, that instead of getting a person to do it for us, we would design some sort of smart heating system. What is that? Well, it's essentially talked about in the bottom paragraph, right? It consists of a few things only, right? It consists of a thermostat. You might not know what it is, but essentially it's just a temperature sensor, right? What it does is it converts the temperature and produce an output voltage that corresponds to that temperature as the temperature changes, right? So if the temperature is high, the output voltage might be high. If the temperature is low, the output of this thermostat might be low. And we use that output to make some sort of a decision, right? So you'll have technologies in your smart heating system that essentially interprets this voltage to indicate whether the temperature is too high, is it too low, or is it just about right. And essentially, the decision made by that would just drive some sort of resistive heating element in the smart heating system. Again, just applying the appropriate voltages and current in order to produce more heat or less heat, depending on what the temperature is at the moment. Right? Notice all this is done without manual intervention, right? That's essentially what we want to do, right? As opposed to some sort of laborious manual labor. Now, hopefully you also see that in order for us to study or understand or even just make use of this smart system, this electronic instrumentation, right, obviously we've got to have a very firm understanding of the fundamentals behind what these electrical quantities means, right? What are voltages and current? How do they behave in a circuit, right? And how do we probe these quantities? How do we predict them in an arbitrary circuit? Only then, once you understand this behavior, can we actually design something or construct electronics that meets what we wanted to do. So essentially, that really forms essentially chapter 2 of the coursebook. Chapter 2, if you looked ahead, you would have seen it's something that I would like to call the tools of the trade. Right? These are fundamental ideas about electrical and digital systems. These are fundamental concepts in which everything we're going to do later on builds upon them. And so this again reinforces the idea how I said engineering is a subject where everything is built on top of everything else. So that's chapter 2. Now, we need chapter 2 because essentially the sort of instrumentations we're going to be dealing with. Now, essentially, that smart heating system reveals the sort of systems that I'm actually talking about. So if you essentially change your course book to page 2, page 2. In fact, I lost my notes, so I'll need to get a book out. Oh, no, it's over here, never mind. Right, if you think about the sort of operations that we just went through about the smart self-regulating heater, it essentially underpins all modern electrical and digital systems. It underpins the internal workings of all modern electrical and digital systems. Which one are they? They are the ones that give some sort of perception of automation and intelligence. And that is the sort of systems that we're interested in. What are they? Well, essentially, if you think about what we just did, they are essentially systems that does 3 things. They monitor, analyze, and respond. Right? These are systems that monitor some sort of environment, convert, if necessary, some sort of non-electrical quantities into the electrical analog. And by doing so, we are able to manipulate that electrical analog by analyzing it for some sort of contextual interpretation and to make some sort of informed decision about it. For example, we would convert temperature into some sort of voltage, and that smart heating system will use that voltage to make some decision about whether the temperature is too high or too low, and ultimately the system would respond appropriately to meet a predetermined purpose, in this case, increase the heating or decrease the heating. And so, the practice, hopefully you can see, modern engineers, comes down to the study, the design, or the make use of, or even engineering these electrical, digital systems of monitoring, analysis, and response technology. It's what we like to call, and that's what we meant by smart engineering. Now, in case it's too long, you didn't read, essentially here, down there, is a block diagram that summarizes sort of the sort of systems that you're likely to see throughout your entire engineering career and what this focus of this course is on. So I would just like to spend the remainder time going a bit more in depth about what sort of technologies that we're actually going to cover in this course and what you can expect. Right, so in order for us to convert some sort of non-electrical quantity into an electrical form, right, we need some sort of mechanism for doing that. And that's essentially the purpose of the monitoring technology. These are essentially devices that takes a non-electrical quantity and record it as some sort of electrical signal that we can do something useful for. So in order to understand that, I will need to teach you a bit about the device in which this does this sort of conversion. And these are known colloquially and literally, technically, as sensors, right? Electrical sensors. Now, some people like to call it transducers. Of course, these two words are really used interchangeably. So this is essentially covered in section 3.1, right? We are essentially looking at how transducers actually work, the circuitry around it that's used to actually do that conversion process. And hopefully you can see in order to do that, we must have some understanding of circuit theory. Again, with reference to chapter 2, where we need a firm understanding. Now, an example would be if you've been following, the development in America recently. America is actually in a crisis on top of Donald Trump. They're in a crisis of aging infrastructures and bridges. So that's mean bridges and buildings that's been built so long ago that their structural integrity are deteriorating, but there's just no way for them to actually monitor the structural health of these infrastructures. And as a result, there have been cases where bridges suddenly collapse without any sort of advance warning whatsoever, and times led to fatalities. Right? In fact, the American Society of Civil Engineering gave the nation's infrastructure a grade of D+. Now, I don't know what that scales on, but it's certainly not something I like to see on my transcript, let alone a building that I walk into on a daily basis. So what we do nowadays is we always embed sensors into the sort of structural members of the buildings that we build. Right? These are known as strain gauges, as an example. So what they do is they actually monitors the tension and compression in the members over time in terms of some sort of electrical signal, so that we could monitor it and give us some sort of advanced warning so that we can take some sort of timely action. Right, so that's sensors. That's what we're going to look at in section 3.1. Now, inevitably, it turns out that the signal output of the monitoring technologies are really small. They're really, really small. In fact, they're so small that we can't actually do anything useful with it unless we can somehow make it larger. And that essentially is the purpose of the analysis technology, which will be covered in section 3.2. So the analysis technologies, the purpose of it is twofold. The first thing is we've got to somehow condition the signal output of the sensors into a form in which they are useful, in which they can be used for the subsequent processes. So the term that we use technically is called signal conditioning, right? We're literally conditioning the signals, which is essentially voltages or current. But essentially what we're doing is we're processing them in some way. And in our case, we want to amplify it, right? Make it larger so it can be used. Now, the device or the circuitry that we do this these days is through a device that's known as the operational amplifiers. I'm not sure if you've heard of it, but essentially it's the workhorse of modern electronics. So that's the first part of essentially the analysis technology that we're going to let you understand the design around these operational amplifiers and essentially to amplify the signal from the sensor output. Now, no matter what the signal is, once the signal is amplified to a form where it can be used, these days we will want to store them on some sort of computer so that we could process them, right? It turns out in order for us to do that, we have to convert that analog signal into a form in which a computer can understand, right? You see, the computers don't actually speak the analog that the output of the sensor produces. In fact, it speaks a completely different language, and so it needs some sort of a translator. And that translator is known as an analog to digital converter. Again, that's something you'll learn about as part of the fundamentals, and that's in chapter 2. And the language that computer speaks, you probably all know, it's known as a digital signal. And we'll really need to teach you about what does that actually mean. And for that, we'll need to teach you a bit about number systems. Again, this is in chapter 2, part of the fundamentals. So then what the hell is in section 3.2 then? Well, the second half of section 3.2 is about the fact that once we've got the signal in a form that a computer can process, well, we need to make some sort of useful decisions out of it, right? We don't just want to store the signal, but we want to do something useful, make a prediction, right? Make some sort of decision, regulate the temperature. So in order to do that, in order to make this decision making, we have to teach you a little bit about how computers make these decisions, and that's through the use of logic circuits. So if you've heard of logic gates before, that's essentially what it is, and that's what we're going to teach you about for the remainder half of section 3.2, but also a little bit on embedded systems and how we actually implement these logic using software, right? So that's something you could look forward to in section 3.2. And finally, once that decision has been made, what we ultimately want to do is make some sort of response, right? Take some sort of action. And that's what the response technologies are for, right? In the simplest form, it generates some sort of action or response to the input, right? In its simplest form, we might simply turn on a light or display a text on the LCD panel, for example, to display some sort of measurement. And for that, we'll have to teach you a bit about visual response technology, essentially how LEDs actually work, and for example, how 7-segment displays actually work. Right, but in more complicated situations, we will also like the system to make some sort of more sophisticated movement. For example, some sort of mechanical movement. And for that, an example would be over here, such that we want to navigate a robot through some sort of plotted trajectory. So for example, we will activate some sort of a motor on the wheel of the robot to do some sort of motion. And that's where the lab actually becomes interesting. You see, the laboratory that you're going to be doing shows an example of this smart system, right? We consolidated this understanding here in a fun way for you to play around with in the laboratory. Now, unfortunately, I forgot to bring the actual robot that you're going to be playing with for the lab, but, sorry, we're nearly done. But what you're going to be doing essentially is you're going to be designing a robot, right? What that robot's going to do is it's going to be put into a maze, and it's going to somehow navigate its way out of the maze without you needing to do anything, right? So you'll notice that it must then have some sort of a sensing mechanism in order to tell it where it is. And depending on what happens to it, say if it hits a wall, well, you've got to design some sort of logic circuit that tells the system what to actually do. And for example, you might want it to reverse its wheels, so that it'll reverse back. In fact, you might want it to turn right or turn left. And that wheel movement is essentially the response technology that I'm talking about here. Right, so hopefully this helicopter view gives you a brief understanding of what you are about to explore for the rest of the course. And look, I'm just excited as you are to bring you through this journey. So I'll see you on Wednesday. Thank you.
That was good.
Could have done better.
There's always better.
Yeah.
Yeah. Unfortunately, there's always worse.
There's always worse too. Yeah, I forgot to bring the robot back.
Yeah, it doesn't matter.
Something like that.
It's interesting. Right on 10.2, they start getting restless and noisy. Yeah.
Something wrong with
Okay, let's get started. Did you have a good weekend? Do you have a lot of things coming up for this next week? Yeah, accounting? No, don't know. Just worried about the midterm, mainly? Okay. Okay, so we'll talk a little bit about a few different things. I first want to go over some forward-looking things, some of the things that we're going to be doing in the future. Then I want to talk about so a lot of that's administrivia. Then we'll talk about the TBL assignment that we just did. And then we'll get into some questions related to the midterm. And I know that's what you're all waiting for. So, without further ado, let me just give you a quick overview of the group assignment that's coming up. So this is the big project that you'll be doing. We went back and forth, the teaching team went back and forth about whether to give you some new data, some up-to-date data, or keep the same data that we've used in previous classes. And we've decided that we're going to keep the previous data for this time around just because this class is really on a compressed schedule, and we don't want anything to disrupt you. I noticed that, if you feel like you're disrupted, then there's hysteria. So we want to keep it the same as much as we can so there's no surprises. So to that end, we're going to study New Zealand's food exports, and the data set includes all records of New Zealand's food exports from 1994 to 2012. And you're supposed to use what you already know, your descriptive and predictive methods, to analyze that data, to make sense of it, and to gain some insights and make some recommendations. So we'll give you an exact write-up about the project soon, but this is just an overview for you. So part of what you need to do is to select your appropriate tools for analysis, and it'll help especially next term, or not next term, the next unit when we talk about regression analysis. That's something you'll probably use for this. And you'll analyze the factors that influence food exports from this country. So there's two purposes here. One, you get to use all of the tools that you've learned about. You get to study real data. And the second advantage of this type of project is that you get to find out a little bit more about New Zealand. Okay, this is something that wouldn't necessarily be published often, but you're looking at the raw data so you can basically make the story. You can figure things out. So the assignment itself will be about 2,000 words. You can use graphs and tables, but use them sparingly, i.e., make sure that they're part of your story. Don't just stick them in because you want to pad the report. After you do your analysis, come up with a narrative and make sure that the image or the graphs that you include support what you're saying, right? They help tell your story, basically. The assignment itself counts for 16%, 11% for the report, and 5% for the presentation. We had played around again with letting you do digital presentations. What we've decided to do is also revert back to how we did it last term and have you do live presentations instead. That might be easier, I'm not sure. When I first mentioned digital presentations, I heard a lot of groans. So I'm not sure if there's a preference for doing live presentations over digital. But this time around, we're going to do live presentations. That also means your time is going to be compressed. In the past, we've done it over weeks 8 and 9, and we've split up the TBLs, and you've had a longer amount of time to present. This time around, what I'd like to do is have you do it in about 5 minutes and be really firm on those deadlines. That's something we're going to have to discuss going forward. I want to get some feedback from you about whether you think that's feasible in a live presentation. Certainly with a digital presentation, it's a lot easier to edit. But in a live presentation, you really have to practice and be on your presentation has to be right on, and that's more difficult. But the advantage is we get it over with, and then you can move on with the course. Otherwise, we have to spread it out over 2 weeks, and it's awkward and whatnot. In the past, they've spread it out over 2 weeks. I'd prefer not to do that, but we'll talk about that, okay, in the upcoming weeks. And again, the report submission deadline is August 26th at 9 a.m. I think that's right. That's the Monday of week 10, I believe. So you'll be dying to get it in. As far as deadlines go, I've learned my lesson. There's going to be a hard deadline. If you have to submit something, you've got to get it in on time, okay? Once Canvas closes, I'm not going to reopen it, okay? So it's your responsibility to get it in on time. Okay. And again, I hope these dates are right. I've altered them from last year's, but I may have missed one or two, so please let me know if I've missed something. Let's see. Yeah, so this is the old way that we organized the presentations, where the TBLs were split in half. I prefer not to do this, but the logistics of this we'll have to figure out. Again, I'd rather have it in 1 week and have everyone do their presentations and get it over with, rather than spread it out over 2 weeks. I think that's more difficult for you and perhaps more stressful. Yeah, that 10-minute deadline is also not right. We're thinking of compressing it to 5 just so we can get everyone done in the same week. But again, we'll see how realistic that is. So I'll try to update that before and repost that. Let's see. Are there any questions about the group assignment? This is just an overview. This isn't written in stone yet, but any questions about that? So basically the same as last quarters. Not a lot of differences. Going once, going twice. Okay. There'll also be a peer review portion of this. Quite often when you work in a group, there's tension, someone doesn't, it's perceived that someone's not pulling their weight, et cetera, et cetera. So we'll give you an opportunity to review one another, and we'll take that into account. This doesn't necessarily become part of your mark, but we reserve the right to make use of this information when it comes time to allocating marks. So again, you'll be able to, it's your chance to give feedback to one another. Now, we expect you to do this throughout the term, not just sort of launch this on someone at the very end. You should be giving your peers feedback so that they can contribute effectively. Each of us might be good at different things, and sometimes you have to help your teammates along and give them an opportunity to contribute. That's how the working world works. That's how life works. So again, you can rate your team members, but you also realistically have to give them a chance, okay? We've had situations where people have said at the very end of term that this person wasn't pulling their weight, but we didn't hear any complaints up to that point. So we can't really take that into account if we don't know there's a problem. And you can't launch it on a person like right near the end of the term when they can't do anything about it. Does that make sense? We'll talk a little bit more about that as well. But that's just your chance of making sure that your team, everybody on the team has to contribute. It's an incentive-based system. So if there's no further questions about any of that, I want to talk a little bit about the TBL assignment. Are there any questions? Okay. first thing I'd like to do, I'd like to talk a little bit about, and just go into this, some of the questions that we used as preparation for the TBL. Let's see if that works. Oh, look at that. All right. Okay. Okay. This is a little dark in here. Do you need it a little bit brighter, or are you okay? Can you make that out? Okay. I know this document camera is not great, but it's hard for me to tell whether it's my eyes or the camera. Okay, so this is the review question that we had prior to the TBL, and I just quickly want to run through it because I think there's some good intuition in these questions. And again, the answers are online, the questions are online. These are things that I gave you the week prior. And I think it's worthwhile just stepping over it again, okay? I'll just quickly read out the question, and then we can go through it. And again, do you want the lights up a little bit so you can write, or would you rather be able to see this better? Yeah, okay. So we'll leave it at that. For the year 2017, 33% of taxpayers with adjusted gross incomes between $30,000 and $60,000 itemized deductions on their federal income tax return. The mean amount of deductions for this population of taxpayers was $16,642. Assume that the standard deviation is $2,400. You wanted accounting questions. Now you got an accounting question. So the first question that was given was, what are the sampling distributions for X bar for itemized deductions for this population of taxpayers for each of the following sample sizes: 30, 50, 100, 400. Does anyone want to sort of walk me through what you gave? This isn't a trick question because the answers are online. Did anyone do this prior to the TBL? I mean, I'm not going to ask you to answer it right now if you don't want to. I know you probably got your answer squirreled away if you did answer it. Okay, so this probably would have been a useful thing to look at. Let's see, I'm going to quickly turn these off and have a quick, this is the disadvantage of the document camera. Oh, actually, you can see that. Okay, and then the second part of the question was, what is the advantage of a larger sample size when attempting to estimate the population mean? So we'll step through part A in just a second, mainly because it's a piece of paper and it's the next thing written in there. But you can already answer part B intuitively. And this is the question that I'm more concerned about, frankly. So what is the advantage of a larger sample size when attempting to estimate a population mean? This is what I'm really interested in because this is the intuition part of it.
Makes any estimation more accurate.
That's right. So the answer was it makes any estimation more accurate. Right? So when we talk about the standard error, we know that it's the sample standard deviation divided by the square root of n. And so as n increases, that standard error is going to decrease, right? We're going to get more accurate estimates. And I hope that's intuitive, because that's a really important idea. So if you have a small sample size, let's say you want to buy, you want to sell shoes. You're an entrepreneur, you're importing shoes and you want to sell them. So, but you want to make sure that the style's right. You go out and you interview 3 people. It's a really small sample size. So how confident are you going to be in those results intuitively? Not very, right? So you're going to have a very, very big confidence interval. If you interview 10,000 people and you get their feedback, you're going to be much more confident in your results. Does that make sense to everyone? Yeah. So, anyone not clear on that intuition? It's all about that estimation interval, right? We just want to make sure that we're, with a high likelihood, capturing the population mean. And we'll come back to this again, but this is really what I wanted you to get out of this exercise as you went through, was just thinking about what happens so if we look at the mean, and then, sorry, my printer is not, or my fonts aren't great. So I called it sigma x. It should be sigma sub x bar. Like it's printed in your book, I just can't do that in Word. But again, you can see the standard error decreases as we increase the number of samples. Right? The mean is always the same, or our parameter estimate of the population mean is always the same. But the standard error decreases as our sample sizes increase. Let me just focus on that. I just want to put this up briefly, just so people who are watching, hopefully this comes through on video. This is a bit of an experiment for me too. I want people to be able to see this who are at home, or you, if you go and review this video, hopefully this isn't too grainy. It looks pretty grainy on my screen, but let's see. Is that better? Okay. All right. It's not ideal. This tablet is my other option, and it doesn't look great either. So we'll have to work through what's the best way of working through problems. But for today, it's going to be the document camera. Okay. So we're all okay with that intuition? Okay. Okay, now this one's going to be a little more, this is the other question from chapter 6, number 18. Again, this is online with the answer. This one's focused on confidence intervals as well. So the average annual premium for automobile insurance in the USA is $1,503. I used to work in the insurance industry, unfortunately, and so that's why. It's as exciting as you think. The following annual premiums, and there was an attached spreadsheet for that, are representative of the findings of the state of Michigan. Did people work through this? Did you have a chance to sit down with this auto insurance? People not super excited about insurance. That's fine too. Okay, so the assumption is that the population is approximately normal, and we asked 3 questions. The first was to provide a point estimate of the mean annual automobile insurance premium in Michigan. The second, and this is really what I'm concerned about, was to develop confidence, sorry about that, interval, not an intern, for the mean annual automobile insurance premium in Michigan. And the final question was, does the 95% confidence interval for the annual automobile insurance premium in Michigan include the national average for the United States? And it gives us that national average. What is your interpretation of the relationship between the auto insurance premiums in Michigan and the national average? Okay. Does this ring familiar? Maybe. Did anyone have a chance to work through this on their own before I discuss it? No? I mean, it's based on a data set, so if you haven't worked through it, then we won't worry too much about it, because we'll have to pull up Excel and all that. I can certainly do that, but again, I really want to focus on the intuition of the confidence interval part, because I think that's really important. I think you can do the mechanics, or from what I saw in the assignment, everyone is capable of doing the mechanics of confidence intervals, and that's great. You can do the calculations. The interpretation part seems to be lacking. Some of you just aced it, and some of you did the calculations perfectly and then misinterpreted the results. And that's really, it's difficult for us to give you marks in that case, because you're only doing half, you've only got it half right. So that's why I want to go over this part. Let's see here. Can I? Is that better? That's a little better. Sorry about that. Okay. So if we calculate this, we can get upper confidence and lower confidence intervals around our sample mean. And just quickly looking at this information, oh, sorry, I'll move this question a little bit back into focus. So now with this information, I'll give you a few minutes to think about it, maybe talk to the person next to you if you're unclear about it. But I just want to give you a chance to sort of take this in. This is more of, this is a question like you might get on the midterm, for example. Okay, so we're not going to ask you to calculate too much, but we'll give you some information of calculations that have already been done, and then say, okay, what's going on here? And explain why. You know, justify your decision on some aspect of this. So I'll give you a couple of minutes to think about this, and then we'll quickly discuss, okay? I'll just cover that up so it's not too confusing. Very high tech. Okay. I get the sense that everyone's kind of settled on this. Maybe we've moved on in topics. Okay. Oh, not that one. Okay. Does anyone want to answer this? Let's see. So we know the point estimate. Can someone, part A? Anyone want to take a shot? Generally speaking, what's the point estimate? I know you know this. Sorry? That's right. So the answer, of course, was the mean. The sample mean here is the point estimate of the population mean. So we've developed 95% confidence intervals. Sorry about that. For the mean annual automobile insurance premium in Michigan. Can someone tell me what those confidence intervals are? It's just going to be me and you today.
Yeah, it's the likelihood of the sample mean being representative of the population.
That's great. Absolutely. So again, this is our confidence interval. So 95% of the time we expect, so if we were to do this multiple times, 95% of the time we would expect the population mean to appear within our confidence intervals. Sometimes, and I think even in the notes, sometimes people, well anyways, we'll talk about that when we come to it. I think there's a slight error in the slides, but that, anyways, the intuition is just that the population mean will appear within this confidence interval 95% of the time. And we did that, we gained that intuition as well when we took multiple random samples in class, and some of you had the population mean within your interval and some of you didn't. Most of you had it within, but I think there was one group, at least one group in one TBL, if not both TBLs, that didn't have it within their confidence intervals. And that's by design. We want you to see that very occasionally you won't have the population mean within those intervals. Does that make sense? I think that's something that we've covered. And again, this is exactly the sort of question you're going to get on the midterm, in that you're interpreting data that you get, okay? What we don't want to do and what we're not going to do is expect you to churn out a bunch of numbers and leave it at that. There's always going to be an interpretive piece to make sure that you get it. Okay, so question C. Does the 95% confidence interval for the annual automobile insurance premium in Michigan, right, so we're looking at a sample of data from Michigan, include the national average for the United States? So how do we go about solving this question? I'm going to make it especially difficult in that I'm not going to ask you. Somebody else want to answer this question?
Check whether the population mean falls within the range. If it falls within the range, then the sample is good to represent.
Yeah, so the answer was, and it's the question, I'll just go over the question and the answer because the answer is right. Does the 95% confidence interval for the annual automobile insurance premium in Michigan include the national average for the United States? So the national insurance average is $1,500. As pointed out, it's not within the confidence intervals. So what does that mean? That's the second part of the question. What is your interpretation of the relationship between auto insurance premiums in Michigan and the national average? So this is, again, taking that next step. Now that we know that this is not within our confidence intervals, what does that mean? Remember, this is the national average in the United States. These confidence intervals are based on a sample from Michigan. So what's that mean? I want to make it doubly hard, and I'm not going to ask either of you.
The sample isn't representative of the population.
So the answer was the sample is not representative of the population. No, I wouldn't say quite that. Sorry?
Not the best representation of the entire population.
Yes, and from that perspective, that's true. In what sense? In what sense is Michigan different?
It's much higher. The mean is much higher than the national average.
That's right. So Michigan, insurance in Michigan is much different than the national average. So insurance rates are much higher in Michigan. Or at least according to our sample. And I mean, we don't know why exactly, but we can take a guess, like maybe Michigan's cold, the roads are icy, maybe insurance rates go up because people have more accidents in the winter. I mean, we don't know. This is outside the scope of the question. But that's exactly right. That's a great interpretation. Because this is the national, of which Michigan is a part. But Michigan is much, much higher. So again, you can think about these things. In this case, drawing is perhaps, not that helpful. But in general, you can think about you have the national average, and then you have Michigan. You have this, and they're not even close. And when you're working with confidence intervals, it's often useful to draw them out, right? Especially if there's some confusion about them. Just, again, you want to get this intuition. You want to understand what's going on in your data. And visualization is often helpful. And we'll see in a minute, though, sometimes visualization is misleading. So to that end, those were the two questions that I gave you there. Let's quickly go back to the lectern. And I want to talk a little bit. Are there any questions about the Michigan insurance problem? Yes?
Why did we not use the distribution for the previous one? Because the sample was quite small.
Yeah, okay. In that question, and there's a write-up on this, in that question, the sample size is very small, and they actually use the t-distribution. We don't use it in this class because I don't want you to have to do the t lookup and all that stuff. So we just use z, the z distribution. Remember in the TBL I explained that the t distribution is a lot like the z distribution, except the tails are thicker, right? And the t distribution is designed for small samples. Now, in a pinch, if you use the z distribution, or the normal distribution, you're not going to be that far off. Okay, you'll be a little bit wrong. But yeah, you're right. And there's a bit of an explanation online about that as well. So you'll see if you load the Excel spreadsheet, I added a little bit of a note about the t distribution versus the normal distribution. If you don't understand what the t distribution is, you can either ask me, but you don't have to worry about it. It's not on any tests, okay? We're not going to, but it's basically a similar shaped distribution to the normal distribution, but it's specifically designed for small samples. And in this course, we're going to assume that all our samples have 30 or more observations, so therefore we're using the normal distribution. For this particular question, there weren't 30 observations. So technically you should use the t-distribution, but I made a note of that explaining why we're gonna ignore that problem for this question. But yeah, good point. Okay, TBL. I want to quickly jump back to the TBL assignment and just go over a few points. Again, these are relevant for the exam. This was a good question in a number of ways because it dealt with interpretation. First thing, I want to talk about descriptions. Most of your descriptive passages were quite good. They could be better. Almost all groups did not have an introduction, right? So I would come to market and it would just be, the average salary is blah, the mode of the salary is blah, and it's hard, you know, if you get up and you get a coffee and you come back to mark, and then you read that, you're just kind of disoriented. What question am I marking again? What's going on? One sentence to just sort of orient your reader. I'm an analyst for Seek.com, and we are studying the relationship between salary and stress in managers in Auckland. Here are our results, right? So one of the things, this is an old saw, if you will, of journalism. If you want to write something, tell people what you're going to say right up front. One sentence, one quick sentence. Then the next thing you do is you say it. You say that thing. I'm an analyst. I'm exploring these variables. Blah. Here's the variables. Here are their relationships. And then at the very end, tell them what you said. And you just conclude. Not paragraphs, just one sentence maybe. But the key idea, first of all, is just give them the introduction. This will change all of your marks in writing throughout university and throughout your professional life. If you tell them what you're going to say and introduce your reader to what you're doing, your marks will go up. Because when people mark your paper, if they see that, they know what you're talking about. Even if the structure within that is a little bit maybe not as good, but if you introduce it well, just one sentence, it will orient your reader and they'll be much more forgiving. So in general, tell them what you're going to say it, and then tell them what you said. Tay probably has more rules than that, but those are the three rules, generally speaking, in writing. Any questions about that? It's a simple thing to overlook, right? Because you're in a test condition and you're in a rush, and I understand that. But it's really helpful to do that. Similarly, little things, descriptive titles. Most of you are quite good on this front. And most of you put the scatter plot, which I thought was great. I didn't take off marks or anything like this, but just in general for your reports, keep that in mind. Be descriptive. Explain to your reader what they're seeing. Don't make any assumptions. Whoops. Okay, correlations. Correlations are a great thing, and most of you had a correlation table, or at least took correlations of some of the major variables. I'm not sure if in your notes you call this high. I don't want to confuse terminology. You know, in case of confusion, refer to your notes. But this is higher, certainly. It's the highest correlation in this table, whereas this one is quite low. And the nice thing about correlation tables is it gives you a quick snapshot, an overview of your data. What are the relationships here, right? So what are the relationships here? Specifically with regards to stress and salary. Yes. Relatively high, certainly relative to, I forget whether you call it medium high, or what we said in the notes. Just, you can follow the notes. But 0.68, closer to 1, sort of at least medium correlation. Depending on the data you're looking at and the context of why you're looking at it, you might be a little loose with these things. It never hurts to report the correlation. You don't have to go 10 digits or something, like 2 decimal places is often enough. And again, you can report that within the sentence. There is sort of medium high, medium correlation relating these 2 variables. What's going on with gender and stress? What does the correlation table tell us for gender and stress? Anyone want to take a guess? Sorry? I thought I heard the answer. Someone? Yeah. Correlation is really low. So that's not my laser pointer. This is, okay. The correlation is really low. And again, that's the great thing about correlation tables is they give you an immediate view of what's going on. And when you do your write-up, by the way, some of you just reported what was significant and what was high, and that's good. But you might also want to mention what's low, just so you can assure your reader that you've done the work, you've done the analysis, and even though you might think there's a relationship between gender and stress, it doesn't seem that that's the case because the correlation is quite low. But let's talk a little bit more about this. If you look at the bar plot of gender versus stress, what do we see? I mean, intuitively, when you look at that, does it look like there's a big difference between the two? I know. I'm not going to ask this row. Your point is right. But many people, I think what they did was they plotted this, and I think that's a good intuition. I think plotting things is good. But unfortunately, they plotted this in Excel, and Excel has this habit of setting it so that it just shows off the difference, right? So if we look at this axis here, we start at 6. Whereas if we were to start at 0, we would see that is maybe a better point for this particular bit of data, because in actual fact, both males and females have very similar stress levels. Like, this is the same data. So they're both 6 something. But the difference doesn't seem as extreme, as you point out, because in the previous graph, or the previous bar chart, that looks quite extreme. But if we take into account, if we lower the starting point, we know that the minimum stress is 1. If we show that, then we don't see that difference. And I think, unfortunately, a few of you got led astray. You did the right thing in that you were trying to visualize the data to make sense of it. But because the default for Excel was 6, you know, it showed off this great difference, and then there were a number of descriptions that sort of veered into this idea that there was a big difference in stress between the genders. Now, if we looked at the correlation table, of course, that relationship is not there. So this is something to keep in mind going forward. When you're looking at these visualizations, you know, what are the default values of your axes, right? Because you don't want to tell a false story. So that's an unfortunate default for Excel. Maybe it helps in some cases, but in this case it was misleading. The other thing I want to mention about write-ups, and this didn't happen often, but in a few cases there was a little bit of, I think it was the stress. You all know that plagiarism is not acceptable. There was sometimes little bits and pieces were taken from the web. Sometimes it was an image and whatnot. I understand that. I understand why one might be tempted to do that, but you have to cite it, right? You can't just copy it and put it in your report. You have to cite where you got it from, right? Similarly, don't take quotes, direct quotes from other papers, et cetera, without quoting them and citing them, okay? There's nothing wrong with taking information from other sources, but there is something very wrong about not citing it properly, okay? And I realize during the TBL assignment, that's a stressful time, and you know, so I'm not going to get upset about that. We're going to use that as more of a learning experience. But in future, especially for your assignments, don't, you know, plagiarize. Don't take from other sources without citing appropriately. Okay? Let's see. Are there any questions about what I've covered in the TBL assignment? That's really useful information, I think, from a descriptive point of view. If you're given a question where you have to make sense of a lot of data or make sense of the results of an analysis, keep those things in mind, you know, as far as how to present your information, your results, you know, always have an introduction especially, et cetera, et cetera. Okay. Now, let's see how much time we have. Okay. So, let's talk a little bit more about this. Done that. All right. I think we've talked a little bit about confidence intervals. Do you want me to go over the confidence interval part of the TBL question, or should we just do a more general review? We're at 10 o'clock right now. I don't want to take up too much more time focusing just on the TBL. Any preferences? Maybe we'll just talk some more about the general. We've already talked about confidence intervals a bit, so I don't want to beat a dead horse. So maybe I'll switch back and we'll deal with just the review. Are there any questions about the TBL? What we've talked about so far? No? Again, really important, you know, confidence intervals, understand how to do them. Look over the TBL assignment again, look at the confidence intervals, try to make sense of that. That's a good question to review. It contains a lot of aspects that you'll see on the midterm, right? Describing what's going on with the data. As far as the analysis goes, especially the confidence interval part, really important. Sorry. So I won't dwell too much on this as far as topics that we've covered thus far this quarter. Measures of association, correlation. I feel fairly confident in your knowledge of this. I think all of, I don't think I've read an assignment where we haven't completed marking all of them yet, but there was certainly a good understanding of positive and negative correlations. I have no reason to believe that that's not pretty intuitive for people now. Measures of association, as they're called. Are there any questions about that before I move on? I think you handled this part of the analysis really well. I think where you got into trouble, again, was where you didn't do a whole correlation table and then just relied on descriptive statistics like these bar charts and whatnot. I think that's where people sometimes got off the rails. So correlation tables are really useful that way to tell a story quickly. So just to quickly go over that again, I'm going to give you a couple minutes to just sort of think about this exercise question, and then we'll discuss very briefly. Okay? I think this should be pretty straightforward for this group. Okay. Oops. All right, does anyone want to start us off describing, summarizing the results of the analysis and explain the relationships between the variables in the table? Does anyone want to just basically give us some intuition about what's going on? Yes, so there's a negative correlation between sick days and motivation. What do you think's going on? When you're sick, you're not motivated? Yeah, they're not in the best shape to work. Any other interpretations or things to notice in this table?
We can't really say the direction of the curve. So I can't say if I'm sick, I'm not motivated, or if I'm not motivated, I'm sick. It's just, I can only conclude that there's a negative correlation. I can't decide which factor is going.
Thank you. That's a great point. Did you hear that? The answer that she mentioned was that we don't know whether being sick causes a lack of motivation or having a lack of motivation causes people to become sick, right? Correlation doesn't say anything about causation, so we don't know the cause here. We just know that there's a relationship. So that's really important to point out. Thank you. Anything else you want to bring up? Yes.
Following two mains, obvious data that although motivation and sick days have negative correlation, however, sick days and productivity do not have strong correlation.
Yes, sick days and productivity does not have a strong correlation. That's right. That's a good point. Anything else? That's important. It helps to tell the story, right? Yes.
Just a question.
Yes.
Will there be any like index when we can say that it's high, like an average or a very low correlation, or a standard index for the interpretation? Or
I think there's a table in your notes. I've been saying whether, like, what is it? 0 to 0.3 is virtually none. Well, I would say a lot of it is contextual, like, which is why I've been pushing you towards your note, whatever it says in your notes, because I don't want to mislead you and then have people come back at me. Because it really depends, right? Like if you're an active researcher and you're researching some sort of social problem, 0.6 is or 0.68 or whatever, that's moderately high for most social variables. And if you're doing a regression analysis, as we'll find out in a couple of weeks, you don't want variables that are highly correlated. That causes too many problems because then you don't know which variable causes which, right? Or causes the effect. So I think when I say something is highly correlated, I'm often maybe not strictly speaking using those exact gradations because it all depends on the context in which you're using it. So that's why I refer you back to your notes. And if you want, I can dig that up too and I can post it and put a summary there and then we can just be consistent about it. But generally, anything over or around 0.5 and up is kind of interest. I'd say sort of medium. And then as you get closer to 1, certainly anything close or above 0.7 would be, I think, highly correlated. Yeah. So that's a good point, though. So again, don't be afraid to say something like this. Just because this is 0.5, that's of interest, definitely. You could say that's sort of medium correlation. I'm not sure if that's how your notes say it, but I'll look that up. So you have, what's going on here? Yes? Oh, no, okay. Sorry. Saw someone twitching their ear, I wasn't sure. Anyone want to take a shot at that? Just before we move on quickly. Seems to be a positive, some sort of positive correlation between productivity and motivation. Kind of makes sense, right? If you're motivated, you'll be productive. If you're productive, one of the productive employees, maybe you're more motivated. We won't dwell too much on that. I think you get it. If there's any questions about that, let me know. I think your point about the how to categorize them makes sense. If you're writing something up, it's always safest to say, describe it however. You could say, relative to the other variables or whatever, and list, put what the correlation is, right? And then the reader can make up their own mind. That's the safest way to go. Put something in parentheses. Statistical inference. So we've talked about this, about estimators. So if we have a sample and we're estimating population parameters, we focused on estimating means. You can estimate a lot of different things. I'm not going to dwell on this. You have this in your notes now. This is online. Are there any questions about this? This was week 4 We try to tie everything together. So we've thrown a lot of definitions at you. Week 4 kind of integrates all of them and adds the part about making inferences about populations based on a sample. Interval estimation. So we talked about standard error especially. Was newly introduced in week 4. Oh yes, and here's the typo. I think someone wrote this quickly. But this is not, strictly speaking, correct, where we wouldn't say we're 95% confident that the population, you can't be 95% confident. You can't be 80% confident or 50% confident, right? But 95% of the time, we would expect, like if we were to iterate this process of taking a sample, 95% of the samples would have the population mean within the interval. But this is a common mistake to say something like this because it's hard to express. But I just want to clarify that. Interval estimation. I think most of you can do most of you can do the mechanics. Focus on the understanding, especially confidence intervals. They might overlap. They might, be distinct and very different, as we had with the point and the interval estimate. And it's important to understand what that means in the question. So think about that as well. Hypothesis testing procedure. We formalized this in week 4 as well. We threw a lot at you, where you can develop null and alternative hypotheses. There's a level of significance that we specify. In this case, we said mostly 0.5 and alpha of 0.5, 0.05 rather, 5%. So if you have a p-value less than 5%, it's probably of interest. And that's the rule of thumb we adopted. There was some discussion of altering and the pros and cons of altering that heuristic, that value. And that's online in the null. When we talked about the type 1 and type 2 errors, that's online. There's a sort of very short, brief discussion about the trade-offs in doing that. So we talked about p-values and the relationship to hypotheses. So a p-value is the likelihood of seeing a given outcome given that the null hypothesis is true. So if we have a small p-value, that means it's very unlikely to see that particular outcome if our null hypothesis is true. So that gives us pause to think that maybe the null is not correct. So that's the intuition behind that. And that's why we reject the null if the p is smaller than alpha, whatever our critical value is. Okay. Any questions about hypothesis testing? It gets complex. I fully admit that. It's a little bit confusing. It's worthwhile thinking about that table of type 1 and type 2 errors that we went over. And that's, again, there's a quick write-up on that. Yes?
Just a question. Alpha,
sure.
Is that just the value that you sort of decide on?
Yes. So in this case,
0.05 or something like that?
Exactly. So the question was, what's alpha? And I think it comes up, but we've referred to it in a variety of different ways. But alpha generally is like 0.05%, or sorry, 0.05 or 5%. And we've said anything that is below that is kind of statistically of interest. That level is somewhat, I wouldn't say arbitrary, but that's the rule of thumb that's been adopted in the scientific literature. So anything that is less than that is of interest. But of course, it depends. It depends on what your question is, right? If you're doing a statistical analysis of something of a medical situation where you could potentially kill someone, obviously you know, you want to make sure that you don't do that. So you might have very high standards in that particular case. Okay. Does that make sense? I know that some of these things I always say it depends, and that frustrates some students. But that's really how it works. Once you get into industry in a particular field, there will be norms established, you know, depending on what you're doing and what are the common problems that that industry faces. So a lot of these things will make more sense once you get into a particular line of work. All right, so here's a quick exercise question we can discuss. I'll give you a couple, and again, here's alpha we just discussed. Is everyone clear on what that is, what that means? I'll give you a couple minutes to think about this question, and these are all posted online, by the way. I'll give you a couple minutes to think about that, and then we'll quickly talk about it, okay? Okay. By the way, you've covered t-tests in your tutorials, right? Yeah, okay. All right, so you've bought a new machine and you want to find out if that machine is more efficient than your old machine. To find out, you conduct a z-test for the difference in mean jars produced by both machines. So what's the form? What kind of how many tailed test is that? Yeah, two-tailed test. And the results are as follows. How would you interpret that? These are all online, by the way.
I'd say there's a significant difference.
Yeah, thank you. So what's the null? That's right. So the hypothesized mean difference is 0. The idea is the null is that the machines are exactly the same. And remember, when we look at a p-value, a p-value is concerned with the probability of seeing a given outcome, assuming that the null hypothesis is true. So if the null hypothesis is true, the mean is 0. But our p-value is what? 0. So how likely is it that the machines are exactly the same? Sorry? Or the likelihood of seeing that results, rather. What's the likelihood of seeing the results? That they're the same, that the mean is 0. I know it's confusing because it's all kind of intertwined. But the likelihood of seeing this result, given that the null hypothesis is true, is 0. So we're so far back in decimal places that it shows up as 0. So that means these two machines are very different. They're producing different amounts. The new machine is producing, is it producing less? Sorry? The new machine is producing, this is the new machine down here. We've got 100 in each sample. The mean is higher, so it's producing more. Yeah. So we have to reject the null, that they're producing the same. Right? Because this mean difference test is saying that the likelihood of seeing this result is 0. Effectively 0. It's minuscule. It's so small that we have a p-value of 0. So that means we reject the null, and that means the new machine, and this is good news, the new machine is actually producing more. I think the way that p-values work is kind of confusing to people. But you just need to think a low p-value means that you reject the null. Because it's so unlikely that you see this result that the null is actually, there's reason to reject it. Yes?
I'm totally confused here.
Okay. I had an epiphany while I was talking to the class that maybe I was making it worse. Okay.
In this case, do we need to calculate the interval, like the LCL and the UCL first? Or you have given us all the results in the table below?
Yes, all the results have given. So you don't have to do that. What you could, I guess, but
you were saying that we accept the p-value when we know that the null hypothesis is true.
the p-value is the probability of seeing this outcome if we assume the null hypothesis is true, right? So in this case, we're asking, are these two machines the same? Are they working? Are they outputting the same amount? And the mean is different. So that's our first clue that something is up, but we want to test that. So we do a t-test. And the results of that t-test are that indeed this one is producing more. So there's a mean difference. So we know the difference is about 18. But is that statistically significant? And that's what the t-test will tell us. And the results are that we have to reject the null.
What if the p-value is 0.5?
Right on the edge. Yeah, that's a great question. In that case, you would say the likelihood of seeing this result is about 5%. So, yeah. So in that case, your question is, right, what if you're right on the mark? Like right on this alpha value? The alpha is our standard of statistical significance. So we might say, in certain contexts, let me put it this way. Generally speaking, it's a convention that about anything less than 5%, a p-value less than 5, indicates statistical significance. That might be different in different industries, depending on the tolerance that they have for an incorrect result, right? So if you're testing medicine that could kill somebody, you want to be absolutely sure. Just not 5% is not an acceptable failure rate for something that could kill someone. So we're willing, you know, our standards might be much higher. But generally speaking, in like the social sciences, 5% is of interest. And in this case, if you just have a sample of 100, you might say 5% is a pretty reasonable threshold. Right? And so it depends on your case. But yeah, I hope that makes sense. So those thresholds are conventions, but generally 5% is the convention that we pay attention to. Certainly in this course. Yes?
So if it is hypothesis, the test is about total test, right?
So, sorry? No.
I mean, the hypothesis test
Yeah?
is about total test, right?
Yes.
So the p-value is also total or one test.
The p-value is taking in it's a two-tailed test.
Total test.
Yeah, the t-test is a two-tailed test in this case.
So that okay, that means the p-value is the left side and right side together.
No. So yeah, that's a good. Okay, so the question was, does the p-value relate to a particular kind of test? And no, you can have a p-value for all sorts of different tests. So it's not one particular kind of test. The p-value is a way of interpreting those tests. So you could set up a one-tailed test, and you could look it up in your normal chart, and then you will get a p-value for that. Do you remember week 3 we went through a series of z-tests where we would ask whether a particular value was significantly different than the mean, and then we'd look it up on that normal table, and then we'd get a p-value. So that was a one-tailed test. This happens to be a two-tailed test. But a p-value is just a way of interpreting those results. I know it's kind of confusing, and again, this is the difficulty of this course, is we have a lot of pieces now, and if you've never been exposed to them, it's confusing to put them together. But take some time to think about how these different things fit together. The key part of this whole question comes down to the p-value, right here. All right? You can construct confidence intervals if you want, but if you're on a test, understand that this isn't like a calculation-heavy midterm. We want you to understand what the p-value is relative to the question. So interpret the question, look at the p-value, and use that to help understand the answer. Yes?
So speaking of the midterm test, are we going to have this kind of very similar questions like this? Then we're going to reinterpret.
We're going to cover the major topics that we've covered in the course. So certainly, p-values are important. Type 1 and type 2 errors are important. Confidence intervals are important. Understanding the implications of the central limit theorem, like question C in our TBL exercise, right? All of those things are important. Interpreting data. It's not going to be a calculation-heavy exam. You might have to do a little bit, but you're not going to have calculators, so we're not going to emphasize that, okay? And if you're confused about confidence intervals, draw them out. You know, here's one, here's the other. Put it on an axis, and then you can see, do they overlap, do they not? If you have two confidence intervals that overlap, they're not different, right? I guess it depends on the question, but in our case with Michigan, the point that we were interested in wasn't in the confidence interval, so we could say that Michigan was much, much different than the national average. All right. Now, all of those are up online. And I think, yeah, you can go through those at your leisure. But the main thing is we've talked about them, and I think I've repeated everything everyone has said so that we can, if you review the lecture as well, you can hear those discussions again. All right? And I'm sorry we didn't get started till about 5 minutes after. I know it's a heavy lecture, but someone else was in here, and so unfortunately we'll be pressed for time from now on as we've got another class just before us. Okay. Thank you very much. If there's any questions, let me know. Hey.
So, if that means that the alpha file is 5%, so that means the confidence interval is 95, right? 95%.
That's our interpret. The p-value is what you're after. That the alpha is given to you as like the threshold for significance.
Yeah. So
Yeah.
If I can infer from it that the confidence interval is 95%, or I can't.
Oh, yeah. Let's see. I think the way to think about that is the confidence interval 95%. 95% confidence intervals. Yes, I guess it is. Yeah. Yeah. Wait. I'm always tired after a lecture. The way to think about that is our critical value, and I guess it is related to the confidence intervals in that way. The key idea is that, at least for the exam, for the midterm, is that if this value is less than this, then if we give you an alpha to interpret it, then if this is less than this, then you reject the model.
Yeah, I just confused about if this alpha is the entire alpha or just alpha divided by 2. That's my.
This is a two-tailed, so the t-test is a two-tailed test. So